First of all, thank you to TRI and to Dr. Mountford for the opportunity to be here. I'm pleased to see so many faces in the audience. When I started my career, if I met people at a party and they said, "What did you do?" and I'd say, "I'm a statistician," the reaction usually was, "Oh, I hated that class." And now I say, "Oh, I'm a data scientist," and people go, "Oh, cool!" So, anyway, I'm going to talk a little bit about some general concepts behind this, and then we've got a few examples, some biomedical and some not, but hopefully you'll find it interesting and it'll stimulate some thought and some conversation. This is a workshop, so don't be shy. If you have questions or comments, feel free to chime in. I'd like this to be interactive where appropriate, so don't hold back. Okay, first, the name. We're talking about data mining. What is data mining? And there is no set definition, but I'll give you a little bit of a flavor here. Back when I was a grad student, the popular term was exploratory data analysis, or EDA. And a professor at Princeton by the name of John Tukey made that popular, at least in the US, and I think in other circles as well. Data mining has become a more fashionable term, but in the computer science literature, you also see the term knowledge discovery. The common theme here is, from a set of data, what can you learn from it? This is not a way of analyzing a controlled experiment. When you design a controlled experiment, you know the analysis. That's part of designing the experiment. And you know the hypotheses that you're trying to test. This is looking through the data to try and find new insights. And so it's a little bit of a scavenger hunt, if you will. And typically we're looking for patterns, we're looking for relationships, we're looking for things that we might not have thought about before. This can be a little bit dangerous when the data scientist goes off and does this unconstrained, because they might discover things that are spurious. And so it's a process that really should be conducted as a team effort, as a collaboration, where some subject matter expertise comes into play along with the data science tools. And I have here a little graphic that will kind of depict the process. So data are wonderful. They're a great starting point, but it's not the product. The data is the beginning. And you need to do some analysis on it to extract meaningful information from that. But we're not done yet, because the information's not useful unless you can convey it to the people that need that information. So tools for visualizing the data, presenting the data, and providing that insight to your community of researchers is critical. And once that's been consumed, you've learned something. So I got this fun graphic off of from a friend a few years ago, and I think it captures the essence of the process. So, tools for data mining. There are a variety of them. I will talk about some of them. Graphical analysis. I want to emphasize this. I cannot tell you the number of times I've talked to fellow researchers, and they've been discussing the new data set they're working with, and they said, "Oh, I ran convolutional neural nets on this, I used lasso, I used two-stage least squares," whatever fancy technique they want to pull out of the latest literature. And I said, "Have you looked at the data?" "Oh, well, I ran this algorithm on it." "Have you looked at the data?" And it amazes me the number of people that have not looked at the data. The basic tools are the most powerful, and there is no substitute for looking at the data. And I'll give you an example in a moment. The second most powerful thing is to use the basic summary statistics, the standard things you learned in that intro stat class that you hated. Means, variances, t-tests, whatever. Because this lets you explore the data. And if there's really something substantial in the data, it will usually pop out using these simple tools. And the more sophisticated tools are to refine that expectation. Next one, linear modeling. I'll give you some examples of this as we go through. This includes all the standard statistical models that you probably learned in an analysis of variance class or a linear regression class. So simple linear regression, multiple regression, one-way, two-way analysis of variance, analysis of covariance. These are all examples of linear models. The point is that something you're trying to understand or predict is a function of several explanatory variables, and you're trying to develop that model. So that, again, is a very powerful tool. It's not new. Least squares goes back to Gauss, so it's been around for a couple hundred years. But old tools are not necessarily bad tools, so don't be shy about using them. Clustering. Clustering is one that is very intuitive. You're basically looking for groupings in the data. And again, going back to this idea of visualizing the data, in 2 dimensions, it's pretty easy to see groupings in the data. When you plot data, you see clumps and say, oh, there are natural subpopulations in the information I'm looking at. That pops out very quickly. When you get into higher dimensional data, it's tougher to see that graphically. There are tools for graphing high dimensional data, and I'm happy to talk about those if you're interested. But the clustering technique is a way of discovering that. And there are multiple clustering techniques depending on the types of structure you're trying to uncover in the data. And lastly, machine learning. Machine learning is the idea of letting the data drive the development of the model. So we're trying to discover here a set of variables that will predict classes or predict responses. And a subset of machine learning is the very popular deep learning. That is the fashionable thing these days. And I will talk a little bit about that later on. Okay, I said I would talk about graphical analysis. This is an example that has been in the stat literature for more than 40 years. We have 4 sets of data here, X and Y, and we've computed correlation coefficients, and it's 0.816 for all of these data sets. And yet when you look at it visually, I think you'll all agree that the relationship is different in each one of these. And so this is the power of graphing the data. Typically, when you hear somebody report correlation coefficient, I think most of us imagine the graph in the upper left. We're thinking of some scatter plot where there is a relationship between the 2 variables, but a little bit of variability. But it could equally be a nonlinear relationship. It could be a very tight relationship plus an outlier, which we see in both of the bottom graphs. And so visualizing the data will help provide insights. It'll help you uncover these problems. And depending on the techniques that you're using then to do your later analysis, those outliers become very important. Outliers exhibit tremendous influence on many of the modeling techniques, and failure to identify them means you could be going down a rabbit hole that you didn't intend to. Okay, I'm going to talk a little bit about machine learning, and then I'm going to get into some examples. In general, machine learning is, again, another term that's not well defined, but it encompasses that class of tools or methods that let you discover data-driven relationships in the data to predict classes, to predict groups. And one of the challenges with machine learning is that it requires labeled data. If we're going to let the data influence us, we're going to let the data inform us, we need a set of data to do that. And a set of data with the outcomes or the labels that we want to predict. So, if I'm trying to distinguish between a healthy patient and a patient with a particular disease, I need instances of data for patients in both classes. If I have only one and not the other, I can't build that classifier. I don't have the information I need to distinguish between those classes. In addition, what are the features that I'm going to use? And hopefully, in your data set, you have features that are meaningful. Part of the challenge of developing machine learning methods is identifying those features and training that model. And we'll have some examples as we go through the presentation here. So, with that, I've sort of covered the preliminaries. If there are any questions, I'm happy to take them. But what I'm going to do now is dive into some examples. And our first example is probably not a topic that you thought you would hear about this morning: thoroughbred horse racing. In the United States, we talk about a set of races known as the Triple Crown. There are 3 3 races. These are for 3-year-old thoroughbreds, and they happen in the spring. And a horse that wins all 3 of these races is known as a Triple Crown winner. There have not been many of them. These races have been going on since around the early 1900s, some of them even earlier. There have been on the order of about a dozen Triple Crown winners, most of them early in the 20th century. There was a drought of Triple Crown winners for 37 years when, in 2015, a horse named American Pharaoh won. This was a success of many factors, but data mining was a key part of it. And so I'm going to tell you a little bit about how that happened. The horse was owned by an investor named IMAGINE2019. He collected, bred, and ran racehorses. He's a very wealthy businessman. And he had one horse they'd been breeding that he was putting up for auction. This is a 1-year-old. And typically at auction, these horses are given a number, not a name, because the ultimate buyer is the one that wants to give them a name. So this was horse number 85. And he had a consultant that was working with him, helping him to pick out who are the good horses, who are the ones that he should be buying when he sells number 85. Now typically the tradition in racehorsing is people will watch the horse run and say, oh, they have a nice gait, they've got a long stride. They'll look at the conformation of the horse and they'll say, oh, there's good bone structure, the length of the leg is good. And they'll look at pedigree. They'll say, oh, well, this horse is a descendant of Secretariat or Seattle Slew or one of the other famous race horses, and say, that's the mark of a winner. Except there are lots of horses descended from these winners that are really mediocre. It turns out that lineage, genetics, is not nearly as important a factor as the folklore would have you believe. And so this one gentleman named Jeff Sater had been trying to develop ways to model racehorse performance and see if he could predict outcome. He came at it as a data scientist. He was trained in business at Harvard, quantitative guy. He worked on Wall Street, did financial modeling, and he got tired of living in Manhattan. He wanted to do something different. He got involved in a couple of different things. One of them was bobsledding, and he made a breakthrough for the American team in Olympic bobsledding by analyzing films of the bobsled races, and he figured out the problem. The problem is that the American bobsled teams were all made up of these big burly athletes, and the winning teams, mostly from Europe, were light, agile people that looked more like ballet dancers. It turns out the heavy people, while they were strong and they would push the sled to get going, in that process they would actually introduce a wobble into the sled that would increase the friction. And he spotted this by looking at videos of the bobsleds. So fast forward a couple of years, he gets involved in racehorses. He starts collecting all the data he can on thoroughbred racing and building his models. And the real breakthrough for him came when he moved to Florida, to Ocala, which is a center for training for racehorses. And he was able to collect data on physiology. So he was looking at things like heart rate and respiration. Well, most horses that are bred for racing have fantastic lungs. But he was able to collect information on the heart. And he actually had a sort of homemade ultrasound hooked up to an Apple computer that he brought around to the stables and collected data. So when it came time to look at number 85, he told Ahmed Zaid, do not sell that horse. Buy any horse you want off this lot, but do not sell that horse. Well, at that point, the horse was already put up for auction, so it had to be sold. So it was sold to an anonymous buyer who was, in fact, the original owner. So he paid himself $300,000 to buy back his horse. So what happened, when you looked at the parameters that were useful in predicting racehorse performance, it was the size of the heart, and particularly the left ventricle. And the reason American Pharaoh was such an incredible racehorse is that left ventricle was in the 99.6th percentile. So the ability to pump that blood through the horse is what made it a winner. And data mining was what allowed them to have the insight to pick that winner. Now, it wasn't just the data mining. They still needed a good jockey and a good trainer and all the right things to line up to get a Triple Crown winner. But without picking the right horse to start, they never would have made it. So, score 1 for data analysis. Okay, a second example, we're going to look at disease outbreak. Something that I'm sure many people in this room care about. Lots of people look at epidemiology and try and study models of disease propagation and disease prevalence. This is actually work that was done by some colleagues of mine at Virginia Tech who were part of a study called Open Source Indicators. The idea behind the study was what information is out there available in the wide world, not specialized data, not things that you need to go have special means to collect, but things that you could go acquire for free or buy commercially. Using that open source information, can we predict things like economic downturns, civil unrest, and disease outbreak? And so they have some interesting insights into disease outbreak. Here's an example. This is actually imagery that the Draper collected of a hospital in Long Beach, California. And I want to invite your attention to the various parking lots. Look at how full they are. And in particular, this parking lot right here is the one that's right outside the emergency room entrance. That is the key to predicting disease outbreak. And today, there are a lot of commercial imaging satellites flying in orbit. There's a huge revolution in remote sensing that's been happening for the past 5 years. Rather than relying on large, expensive satellites to collect imagery of the Earth, several companies have been putting up literally hundreds of small satellites, much less expensive, orders of magnitude less expensive, that can collect imagery every day. And so pretty much every place on the Earth now can be imaged multiple times a day, depending on cloud cover. There are algorithms, and this is where the data mining comes in. There are algorithms that can process those images and detect objects of interest, and in particular, machine learning algorithms that are used to detect cars. And here's an example of a simple one. We have on the right the parking lot, and on the left the cars that have been detected. Basically, it's detecting pixels that are car-like and painting them white on the black background. And so you can see it does a pretty good job of finding the cars. So we can count cars. It's putting that information together with the location of the parking lot at the hospital that's the key. And so the insight that the folks at Virginia Tech had was, if they look at the changes in the parking lots at clinics and hospitals and similar medical facilities, do they see a sudden rise, a sudden blip in the data? And if they do, that's an early indication of disease outbreak. And they've tested this against data from CDC for a variety of diseases. Primarily, they were using data from Latin America, all over Latin America, and they were getting very good results. And here's the reference to the paper if anybody is interested. Okay, so those are a couple of examples of data mining, some insights that should come out of this. In the first example, the horse racing, one of the things that Jeff Sater was able to do was he was able to do frequent experiments. Because he was actually working in Florida where the racehorses are being bred and trained, he could develop a model, and then he could go watch the races that day or the next day and look at the results, and he could do this frequently and update his model until he honed in on the right factors in the right model. So repeat experimentation with new data coming in. That's one of the keys to data mining that makes for a successful approach. And that's what Amazon and Google do all the time. You'll hear people at Google talk about their experiments. They describe what's called A/B testing. And it might be that they have a particular ad they're going to place on your web page, and the question is, should it be in the upper left corner or the upper right corner? And they'll do experiments where 100,000 people at random get the ad in one corner or the other corner, and they'll look at how many click-throughs they get So they very quickly, in a matter of hours many times, can get feedback by doing these experiments because they have access to a new stream of data. So access to a stream of data that lets you do experiments, key thing for a lot of the data mining that's being done today. In the example of disease outbreak and looking at cars in parking lots, the insight here was looking at a behavior that people can observe, but looking at in a new way. It's like, why is the parking lot full or empty? And what does that relate to in terms of underlying processes? Again, these are insights that people are taking advantage of. And similar work is being done, again, at places like Google. Google Trends, for example, looking at how people are searching their data. That provides insights that are often not available from other sources. There is an interesting book that I read just recently called Everybody Lies. And it was looking at the search terms that people used after Obama was elected president in the US. And I won't repeat the search terms because they're really not polite, but there were a lot of terms that cropped up in Google searches that would let one have some insight into the level of distrust for an African-American president, the level of discontent. And these are not things that showed up in polling data. People don't want to confess that they're racist, but the Google search terms tell no lies. And so data mining that type of information provide tremendous insight. And from that, you can actually predict the success of a candidate like Donald Trump in a subsequent election. So taking advantage of existing sources of data in unexpected ways. That's one of the second key insights that I want to leave you with. Okay, now we're going to turn to some more traditional medical applications. This is from a study that I was involved with at Walter Reed Medical Center and the Naval Medical Research Center in Washington, D.C. One of the outcomes of the two big wars that the U.S. and others have been bogged down in is the increasing number of limb casualties. So something happens, a soldier is attacked, an IED explodes, they lose an arm or a leg. The good news is that tourniquet usage has been very high, so they save this person's life. They put a tourniquet on immediately and get that person out of the battlefield. Wonderful. The sad news is that they're losing limbs because of this. The tourniquet's left on too long, there's ischemic and reperfusion damage because of that. And so the goal of this study was an animal study to see if we could understand that process better. And so, to some extent, it was a design experiment. The idea was, we're going to put tourniquets on pigs, we're going to collect all kinds of data, and we're going to see what insights we learn. Well, that makes sense, but the insights were not obvious a priori. And so they collected the data on blood count, blood chemistry, all sorts of things that you would normally want to measure for a large animal study. They looked at outcome, and they looked at outcome a couple of ways. They looked at pathology, so they had a fairly objective measure of outcome. They also looked at functional outcome, something called the Tarlov score, which is basically a score from 0 to 5 of whether the pig can stand up and walk around like nothing happened, or they're stuck lying there on the ground because they can't move. Those are sort of the extremes of the Tarlov scale. And one of the things that they collected in this experiment was imagery. They had two video cameras, one collecting color imagery, one collecting thermal infrared imagery. And that turned out to be incredibly useful and provided some insights, and I'll talk about that in a second. So let's talk about outcome first. We've got two ways of measuring it, and it turns out they're related. So what you see here in this graph, each dot represents one of these pigs. The blue dots are ones where the ischemia was induced by occluding an artery, and the red ones, the ischemia was induced by tourniquet. And this functional score, this Tarlov score, runs from 0 to 5, where 5 is normal, healthy, fully functional. The pathology score here was basically a mean across multiple tissue samples from different organs. And so what you see here is these animals here that had the tourniquet left on for a long time, 3.5 to 4.7 hours, those were the ones that really had unfortunate outcomes. They lost functionality and they had higher pathology scores. And we actually did a transform of this two-dimensional data down to a single dimension in order to get a measure of outcome, and I'm happy to talk offline about the details of that. But imagine essentially a line going from here down to here, and the further out you are on the line, the worse the outcome is. Okay, so with all the rich data that we had from measuring physiology and blood chemistry and so forth, could we predict outcome? Our goal here was to predict outcome because that might provide insights about how to manage the tourniquet. And the answer was yes, we got a model. We did this by using a very simple data mining technique. It was called stepwise regression. And so the idea behind stepwise regression is I have a whole bunch of possible explanatory variables here. These were all the various physiological measurements and blood chemistry measurements and so forth. I have the measurement of outcome that I want to model. And I look among all these variables and say, what's the best predictor out of all this? And I put that first best predictor in the model. So that's step one. Step two is now, given that that's already in the model, what's the second best predictor? And I continue until I don't improve the fit of the model. And there are some standard techniques, and for those of you who work with statistical packages, there's probably a routine in there that will do this for you. So it's a very easy thing to apply. What it lets you do is explore data very quickly and very systematically and identify the factors that are useful. One of the challenges here is often there is collinearity among different measurements. For example, if I'm measuring monocytes at 60 minutes, well, the measurement of monocytes at 55 minutes is probably highly correlated with that as well. And so which one goes in the model? Well, this technique picks the one that fits best. If you ran the experiment a second time, it's possible that just due to some random variability, it would be the other explanatory variable. So there is an issue here of model refinement and model validation. But the good news is we were able to put together a model, get good performance. The R-square is 0.88, so we're explaining almost 90% of the variance in the data from these factors. Great, we have a prediction model. The only problem is to actually use this in practice, we need to apply these very invasive measurements of blood chemistry and so forth. So enter the imagery. The imagery, it turns out, also provides tremendous insights. The color imagery provides a measure of blood oxygen. Basically looking at the relationship between the red and the blue channels of color imagery, you can measure blood oxygen. And you can do this with a webcam. If you want to go back to your desk and experiment with this, there are folks that have done this. You can look at your own pulse in a webcam because of the fluctuation between red and green. So we pulled out the information here on blood oxygen and looked at how the oxygen level went down during the ischemia period, how it rose during the reperfusion. The thermal imagery is telling you something about the apparent temperature of the limb. And so when the blood flow is cut off, the limb gets cool. When you release the tourniquet, things start to return to normal, but they don't return to normal uniformly. And that's the interesting thing here. So if you look at this IR image early in the reperfusion process, you see variations. You see some of the vascular structure here because the warm vessels where the blood's flowing show up as brighter compared to the surrounding tissue. And so that level of variation in the limb tells you something about the reperfusion process. And so from two simple measures from the imagery, we were actually able to produce a prediction model that actually outperformed the other one. It had a slightly better R-square and doesn't require any invasive measurements. So here the data mining process led us to a possible way to do tourniquet management based only on essentially cameras, things that you can put in your iPhone. And so the next steps now, and what the folks at the Naval Medical Research Center are doing, are looking at ways of developing these devices and taking them to emergency rooms and field hospitals and so forth, and collecting data now in humans to see if they can develop strategies for better tourniquet management. So, data mining led to the insights that led to the next steps that hopefully will lead to better care for these kinds of limb trauma injuries. Okay, chronic pain. Dr. Mountford talked about this yesterday. I'm going to repeat some of what she showed, but I want to talk about more from the standpoint of the data mining. So the idea here is we're going to take advantage of magnetic resonance spectroscopy, and we're going to use that information then on subjects with and without chronic pelvic pain to see if we can identify features that will lead us to classification. Now, the process that we use is the one that was developed at Draper, and this is, in some ways, a classic data mining and machine learning technique. We start off from the raw signals, and we want to discover the features that are useful. So we do pre-processing on the data first to get it into the form that we want to use. In other studies, we've done more extensive pre-processing because we actually go back to the raw Twix files. In this case, we started from the RDAs, so we did less of that pre-processing. But the idea is you want to get clean data to work with. Once we get that data, the technique that we apply is to do a wavelet decomposition. And now we have lots of wavelet features. And the question is, which of those wavelet features are useful for classification? And so we do an initial selection based on simple statistics. Remember what I said at the beginning? Simple statistics are your friend. So we do t-tests to do an initial screening. Throw out all the features that don't show anything in the t-tests. Now, the ones that pass that may still not be good features, but at least you've got a smaller set of candidates. So this is another aspect of data mining, is how do you take a large mass of information and sift it down to something that you can start to work with. And so that initial screening gets us down to a much smaller set of features that we can now evaluate. We evaluate them by developing a classifier using a forward selection process. So it's very similar to the stepwise process I talked about in the previous example, except it's for a classifier now rather than for a linear model. But we pick the feature that fits best, put that into the classifier, see what the results are, and continue to add features until we get the desired performance. Now, choice of classifiers. I know that convolutional neural nets and other deep learning techniques are the hot classifier of the day. But in my opinion, for many of the problems that we're dealing with, the choice of classifier is far less important than all the work that leads up to that classifier. And if you heard my discussion at this conference a couple years ago, I showed some examples of that. I'm sorry I didn't put those into this presentation, but I'll try and describe the issue here. And that is, in feature space, imagine that you've got two classes. If you pick features where those classes are clearly separable, clearly distinct, it doesn't matter what classifier you use, you're going to pick them apart. And if you have overlap in those features, it doesn't matter what classifier you use, you're not going to be able to separate those. Now, there are some techniques, some classification techniques that are used to take this overlapping data and try and find ways to represent it and start to pull them apart. Support vector machines, for example, will take that apparently overlapping data and try and re-express it in a higher dimensional space where you can see differences. But in general, if you've got the good features, it doesn't matter what classifier you use, you're going to be successful. And if you have poor features, you're going to have trouble. And so I want to leave you with that thought. In the chronic pelvic pain example, we had a fairly small set of data. And so in order to test the classifier, we actually used a technique called cross-validation, which I know many of you have applied. The idea behind cross-validation is I take my data and I partition it into two sets. I take a pile of data and put it over here and use that for training my classifier. And then once I've trained it, I take the data over here that I set aside and test it and see how it does. And I do that multiple times for different partitionings of the data. That's a standard technique that gives you an idea of how your classifier will perform on new data. It's not ideal, The ideal would be if you have enough data to develop your classifier on one set of data and now take completely new data and do your testing on the new data. But in the absence of that larger data set, then this cross-validation technique is commonly used and will give you good insights. The one thing you don't want to do is you don't want to develop on the entire data set at once. And that includes the feature selection. I've seen examples where people will do their feature selection using the full data set, and then they'll use, to train the classifier, they'll do the cross-validation. At that point, they already know the answer. They've picked the features based on all the data. So that's not a technique you ever want to use. And if you see somebody doing that, slap them. Okay, so the punchline, the results were very promising. We had good performance on these classifiers. Again, we tried several different ones. LDA is linear discriminant analysis. It's a linear technique. Basically, it takes your feature space and puts a hyperplane through it to separate the classes. And it's been around for 50 years or more. I mean, it's a standard multivariate statistical technique that's been with us for a long time. Very powerful technique. It has a limitation, though. We're doing the separation based on this hyperplane. So if things are not linearly separable, you won't do very well with LDA. Well, it turns out, in this case, things were linearly separable, so we did pretty well. And then support vector machine. Before the big deep learning phase, support vector machine was the hot thing. That was the classifier du jour. And if you look back in computer vision conferences 5 years ago, every paper was using support vector machine. Now they're all using deep learning. So, okay, and here's what things look like in feature space. And again, visualizations are useful. Here you can see that things are linearly separable. Again, small number of subjects. You know, will this hold up when we go to larger samples? We hope so, but part of the process of science now is to take this discovery and to test and validate on new data. An additional insight that came out of this work that Dr. Mountford talked about yesterday was looking at the relationship between these features and the level of pain. And so here are the scatter plots, and again, looking at correlations. And you'll notice these correlations look like what, these plots look like what we want plots to look like. They are relatively linear relationships with some scatter, not systematic functional relationships that differ from linear. Okay, that's chronic pelvic pain. No workshop on data mining would be complete today if I didn't talk about deep learning. So I'm going to finish up on a deep learning example. This is work that a colleague did at Draper, and I helped him a little, but mainly my contribution was the PowerPoint, because that's really my technical specialty. Some of you are probably familiar with the ADNI data set. This is a huge data set on Alzheimer's patients, publicly available. It's free for the taking. You have to register to download the data, and there is a requirement that you, if you publish on this data, that you provide them a pre-publication copy. But with those caveats, anybody can go out and make use of the data. And it's wonderful. They have data from multiple imaging modalities. They have demographics, patient outcomes, and it includes healthy subjects, patients with mild cognitive impairment, and patients that have progressed to full Alzheimer's. And so it's a tremendous resource to use. Now, one of the interesting things about Alzheimer's is there is a belief among many people in the research community, and this is way beyond my pay grade, but smart people have offered these conjectures that it's really not a single disease, but a collection of different diseases that affect cognitive function in different ways. And to quantify this, one of the things that is done is to give a series of cognitive tests to subjects that may be at risk of Alzheimer's or progressing into Alzheimer's. And so this is the battery of cognitive exams. They all focus on different aspects of people's mental skills. And when you roll them all up, you get an overall cognitive score. Well, people have looked at whether they can predict this overall cognitive score and gotten some nice results. Our contribution was to see if we could predict the various subscores. And the reason we're interested in predicting the subscores is that may tell you something about the nature of the disease and the progression of the disease. People do not necessarily progress uniformly across all the various cognitive functions. And so if we can actually identify where degradation is happening, where people are at risk, then we may be able to target the treatments in better ways. So we looked at the data for the various cognitive subscores, and we developed a classifier. We did this using a convolutional neural network. So we had 3 convolutional layers followed by 3 fully connected layers. And the cool thing about this is we did very little pre-processing on the imagery. We don't have to do feature selection, the kind of process that I described with the chronic pelvic pain study. Here we take the raw data, we do skull stripping, so we basically limit what we're doing to the region of the brain, and a little bit of data normalization, and that's it. And so those are standard techniques that are always used with this MRI processing of this type of data. That's what we feed into the architecture, and out pop the results. So how did we do? Well, what you're seeing on the left are the root mean square error for the predictions, and they're pretty low. The lighter blue bar is the forecast, so we're looking at what would their cognitive subscores have been 6 months out, a year out, 18 months out. One of the nice things about the longitudinal data in the ADNI study is that you have, in many cases, years of data on these subjects. And then the dark blue bar is the nowcast. How did our prediction from the model compare to the measured value? So you'll see that the root mean square errors here are quite low. There are still some issues, and I'll highlight them: number cancellation, word recognition, delayed word recall, and word recall. And if you go back here and look at what is causing the problems, it's the particular cognitive tests associated with learning and memory. So there's probably something in learning and memory that we're not capturing in our current model. And that type of feedback then should guide the next stage of development. Now looking over here at the correlation, this is basically the correlation between the measured value and our predictions. And again, we're doing pretty well with the exception of test instruction recall for the forecast. For the current period, we do pretty well in that correlation, but the one value here is surprisingly low. So, takeaway from this: deep learning, very powerful set of tools. You can take advantage of a number of capabilities that are out there in the community. There are tools that you can download for free. PyTorch is one. If you work in Python, TensorFlow is another. You can go out and install these on your laptop and do all sorts of damage on data. Now, that's my last case study. I want to talk a little bit, just in the broad sense, about what does all this mean? And how are we doing on time? Oh, we've got plenty of time. Okay. So, I only have one slide of conclusions. Many people have heard this phrase, data is the new oil. Data is valuable. Data is really valuable. The data that you folks are sweating to collect in your experiments, that is a gold mine. And it's a gold mine because you can apply these techniques and get new insights. The reason Google is a multi-billion-dollar company is because they collect gobs of data. They have tremendous resources to collect data on the behavior of consumers. Amazon, the same thing. You know, the explosion of online information is staggering, and being able to take advantage of that source of information can provide businesses with all sorts of insights that can lead to making lots of money, and hopefully, in the fields that people in this room are pursuing, save lots of lives. So, second thing, there are a lot of tools available now. It is both a curse and a blessing because it enables people to do things without necessarily having the background and foundation to understand what those tools are producing for them. So I encourage folks to work with your data scientists, your computer scientists, your statisticians, your mathematicians to understand what those tools really do. But it's possible to apply a wealth of tools to data and get results fairly easily, much more easily than one could 10, 20, 30 years ago. The last thing I want to stress is we're talking about data mining in this workshop. We've talked about taking data and exploring it and discovering relationships. Discovery is not validation. If I get some insight from a set of data, that's wonderful, but until I can test that, it's not real. And the horse racing example is a great one. When Jeff Sater developed his model and he realized that the size of the left ventricle was the key variable, he then went out and tested that on the next bunch of races at the tracks in Florida. And so he was able to validate that process. And that's what we want to do in data mining, is get the insights from data that exists, data that might have been collected for completely different reasons. Retrospective studies of clinical data, for example. Get insights that then can guide the development of an experiment that lets us validate those relationships. And that validation is the key. Now, that validation is the key for many things. One is it's understanding that the relationships are real. And two, it's trying to understand the science behind it. These techniques for data exploration will let you see relationships, but they won't tell you why. And that's where the subject matter experts come in. And I think that the process really requires a multidisciplinary approach. It requires computer scientists and statisticians and mathematicians to work the data problems, but without the folks that understand the radiology, the medical imaging, the clinical applications, the foundational biology, you're only solving half the problem at that point. So you really need the whole team. And I would like to just conclude there, and we've got time for some questions. Yes, sir.
Hi, John. Thank you for a great talk. I just wanted to ask you a question about the feature selection part. Feature selection is something that I've found really challenging. And you presented some really nice data, the spectroscopy data. I hadn't thought about this sort of, it sounded like you took a stepwise linear regression approach to selecting your feature.
Exactly, yeah.
I was just wondering, does that suggest, and that was effectively a sort of linear discriminant analysis classifier.
Right.
But is that perspective, if I took that approach myself with my data, would that lead me towards finding sort of not multivariate solutions, but sort of individual linear solutions? Is that shape the
Right.
viewpoint?
Yeah, so that's a great question. Feature selection is a challenging area. The methods that we apply are forward selection, so we're starting from scratch and picking the best feature and adding them one at a time. An alternate approach is to start with everything in the model and take them out one at a time. In general, those will lead you to different sets of features, and that's one of the things that people find disturbing. I find it disturbing. It would be nice if we had a technique that said, this is the set of features, but that doesn't exist. There is a huge literature on feature selection. The particular technique, when we start to get to these more general classifiers, the particular technique that I've kind of latched onto is called MRMR. It's minimum redundancy, maximum relevance. And so you're trying to pick the features that are most relevant to the classifier you're developing, the things that have good explanatory power, but minimize redundancy. So if I've already got one feature in there that explains a certain factor of behavior, I don't need another one that explains the same factor. I need something new. Or the way I think of this MRMR process is, I want you to answer two questions in that feature selection process. Tell me a feature I care about, and tell me something new. And that's the process. Yes.
Thank you for the very insightful talk. Actually, I have two questions regarding the Alzheimer's disease prediction. Is the network just like collecting information from the whole image, or is being guided, or it can learn by itself to look at a certain section of the brain? And the other question is, as with this sort of computer-aided detection or diagnosis system, how much do you recommend radiologists depend on it, or like do they decide by themselves, or like how it can be used to help them to make decisions?
Okay, so let me answer the first question, which is the degree to which we were looking at specific regions with the brain. We in fact fed the whole image in and used that to develop the classifier. But one of the insights that people can gain is you can then go back and look at what features did that deep learning algorithm use. So take that architecture and peel back a layer and see what's in the second layer down, what features are there, what regions of the brain are lighting up for the different cognitive subscores. And I think that's tremendously valuable work. We just didn't have the resources to do it for this study, but I think that's a very logical next step. Now, as for the radiologist and how much they depend on it, there is a huge issue in this whole area of automation, and it's not just in medicine, but in reliance on any automated system, and that's trust. How do we know when to trust the system? And particularly with these things that we perceive as black boxes, very complex systems, it's a real issue. We've come to trust our cell phones because we use them all the time. We know that we can punch in a text and it's going to go to somebody most of the time. And if it doesn't, we look and say, oh, well, I have no bars on my phone. No wonder the text message didn't go. But that trust didn't come overnight. That trust came through people using it and exploring it and finding that they could ultimately rely on it. And I think we need to find ways in radiology as well as in other fields to work on those trust issues with automated methods. Visualization and to the degree that we can have transparency in the methods, I think that's a big part of developing that trust. And I would love, maybe 2 years from now at the next IMAGINE, we can have a workshop on user-machine interaction, because that's really a huge part of what's happening in the AI world right now. Okay, thank you very much.